Evidently there was a typo in one of the previous slides that we should fix here to start with. Yeah, the typo is I wrote an next to a direct product there and I should not have. I don't know why I did that. Okay, it's not letting me change it. When S and T are relatively prime, this should be isomorphic to UT. Okay. All right. That last fact that I talked about at the end of lecture A, this one here, is actually useful for a particular example right away. Let G be S3, for example. Group of permutations. It's got these elements. Actually, that's not the example I wanted to do. Sorry. Let's go ahead and think about this example anyway, and then we'll go on to an example that's relevant for this one here. And H be A3, I only want even permutations, right? These three things, those 2 cycles are odd permutations. You're writing them as 1 2 cycle, an odd number of 2 cycles. The 3 cycles are even. They have order 3, but as permutations, they are even permutations because you can write them as a product of an even number of 2 cycles. This is the same as 1 3, 1 2, and this is the same as 1 2, 1 3. So those are even permutations. By the fact that I wrote over there that I erased about the index of H and G here, the index of A3 in S3 is 2. 6 divided by 3 is 2. By that fact that I erased, A3 should be normal in S3, and that is true. Can you also verify it either with the normal subgroup test or with the definition? Actually, let's think of it in terms of the definition. This thing right there. Every left coset should be the same as a corresponding right coset. So for example, the left coset containing 1 2 3, actually let's do it this way, the left coset containing 1 2 should be the same as the right coset containing 1 2. However, that doesn't mean 1 2 commutes with everything. In fact, it doesn't. The center of this is just the identity. Let's go ahead and write out and see that these are still the same coset. So I'm composing 1 2 on the left here with the left coset. I'm looking at A3 as well, so I first compose this with the identity. Then I compose it with 1 2 3, that 3 cycle. Then I compose it with 1 3 2. And let's see what I get when I do that computation. Simplify. The left coset containing 1 2 does indeed contain 1 2. What are the products of these things? Go right to left. 1 maps to 2, but then 2 maps back to 1. 2 maps to 3. Stays fixed with that one. 3 should map back to 2. It maps to 1 with this one, and then 1 maps back to 2. So ultimately 3 maps to 2 with the composition. And with this one, we get 1 mapping, first of all, to 3, and then 3 stays fixed. So ultimately 1 maps to 3. 3 maps to 2 first, but then 2 maps back to 1, so ultimately 3 maps to 1. And 2 should stay fixed. 2 first maps to 1, and then it maps back to 2. There's the left coset containing 1, 2. The right coset containing 1, 2 should be the same set. I am composing by 1, 2 on the right now. And yeah, it doesn't commute with 1, 2, 3 and 1, 3, 2, but in the end, the set is the same. Do this composition, again, right to left. 1 first maps to 2, then 2 maps to 3, so ultimately 1 maps to 3. 3 stays fixed with this one, but then maps to 1, so ultimately 3 goes back to 1. 2 should stay fixed, does it? First it maps to 1, and then it maps back to 2. 2 does stay fixed. We get the 2 cycle 1, 3, which is the same as what we got there. This last one, if these are going to be equal, should be 2, 3. Does 1 stay fixed? First it maps to 2, then it maps back to 1, so 1 does stay fixed. 2 maps to 1, then it maps to 3. 3 stays fixed, then it maps to 2. There we go. These things occurred in different orders in these sets, but when you think of them as sets, the order doesn't matter. These are the same sets. So there's one example where a left coset equals a right coset. If I was going to verify that A3 is normal and S3 in this way, I'd have to do that kind of thing for each element. Although with the identity, it's trivial. Right? Even though 1, 2 doesn't commute with 1, 2, 3 or 1, 3, 2, it does give you the same set. This is true. All right, the other example that I wanted to talk about to illustrate that fact that I mentioned at the end of lecture A, this fact right there, is a more complicated example, but it's worth thinking about. Let G equal a 4 alternating group on 4 elements that's got how many elements in there total? How many elements in this group? 12, right? 4 factorial divided by 2. S4 has 24 elements, 4 factorial. This is the subgroup of even permutations on 4 objects. And let's let H equal, in the book's notation, alpha 1, alpha 2, alpha 3, and alpha 4 is going to be what H equals. But what is that? Alpha 1 is the identity. These 3 things are products of disjoint 2 cycles. 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. The book gives you a Cayley table for A4 on page 105. That's something you should have looked at periodically. You can look at it now if you want, page 105. Claim here is that H is a normal subgroup of G. H is a normal subgroup of A4. It does not have index 2. Coming back over here, A4 did have index 2 in S3. Excuse me, A3 did have an index 2 in S3. But coming back over here, H does not have index 2 in A4. A4 has order 12. H has order 4. The index of H in G is 12 divided by 4 is 3, not 2. So we can't use that fact that says that when the index of a subgroup H in a group G is 2, then H must be normal in G. But I claim this thing is normal anyway. And this fact is actually the quickest way to see it. this will follow if x inverse is a subset of H for all x in A4, you might think, okay, so do I have to check that this is true for every x in A4? No, you don't. If you use this fact, you can get the answer pretty quickly. Why? This group here, this subgroup of A4, is the only subgroup of A4 that has order 4. Why? Well, any subgroup of A4 is going to have to be isomorphic to either, I should probably write that out, any subgroup of order 4 in any group, for that matter, is isomorphic, we know, I mentioned this before, to either Z4 or the external direct product of Z2 with itself. Those are the only two possible isomorphism classes for groups of order 4. But wait a minute. Groups of order 4, subgroups of order 4 have generators, elements of order 4, in fact 2 of them. But A4 doesn't have any elements of order 4. Now it's got order 1. These 3 products of disjoint 2 cycles has order 2, each of them. Right? Square these things, you'll get the identity. And the other elements of A4 are all 3 cycles that have order 3. Like 1, 2, 3, and 1, 2, 4, etc. Those are the other 8 elements of A4. There are 3 cycles which have order 3, not 4. So in fact, H must be the only subgroup of order 4. It's got the only 3 elements of order 2 in it. The other elements all have order 3. Since H must be the unique subgroup of order 4, and it is isomorphic to that, not that, it's isomorphic to that because it's got 3 elements of order 2, and those are the only 3 elements of order 2 in A4. It follows from the fact on the screen that x inverse, which is a subgroup of G, no matter what x is, must be in fact a subset, and in fact a subgroup, and in fact equal to H. I'll just put subset because that's what the normal subgroup test says. For all x in A4. Done. You get it? That might rank near our top 4 most interesting proofs. Our top 3 here that we've been talking about recently. You don't have to actually check this. Any subgroup of order 4 must be isomorphic to this. But A4 has no elements of order 4, so there is no subgroup of A4 isomorphic to Z4. The elements have either order 1, 2, or 3. So this must be isomorphic to this. And in fact, that can be the only subgroup isomorphic to this because it's got the 3 elements of order 2 in it. H must be the unique subgroup of order 4 in A4, and therefore it follows that this is true by this bullet here, that x inverse is going to be a subgroup of H. Subset, in fact, even equal to H. When H is normal in G. Well, okay, so I was using this first fact actually. X inverse is going to be another subgroup of G, but in fact, in this case, it has to equal H. Remember when we talked about the product HK last lecture? and I said this is in general not a subgroup of G even when H and K are, where, well, there's a special case when it is a subgroup. If K is a subgroup of G and if H is normal in G, then HK is going to in fact be a subgroup of G. And the roles of H and K can be switched around. You could assume H is a subgroup of G and you could assume K is normal in G. And this would still be true. That's another useful fact to file away. All right, we're on now in our last 11 minutes to the idea of a factor group. Perhaps the strangest concept of all, but it's also really cool. What is a factor group? Also called quotient group. In fact, again, I have to work hard to say factor group instead of quotient group. Let G be a group and let H be a normal subgroup of G. Then the collection of all left cosets of H and G forms a group under coset multiplication. This collection is denoted by this fractional kind of symbol. When you see this symbol, you can be wordy about it, and you can say, hey, that is the factor group of H and G. For short, people typically say G mod H, to use the word mod, just to say it quicker. And with arithmetic examples, it is related to modular arithmetic. In general, even if G and H are not related to the integers, people often still say G mod H for short. But if you don't like that, you can always say it more in a more wordy way. That's the factor group of H and G, or the quotient group of H and G, or as the textbook, the factor group of G by H. That seems a little strange to me. I typically say H in G. Symbolically, there is what it is as a set. And here's how you do the coset multiplication. You want to multiply two left cosets, AH and BH. What do? It's another left coset of H and G. It's ABH. Or in additive notation, if your group operation is addition, group operation is addition, then you'd write this kind of equation. Writing AB like this, that is a literal multiplication in G. When you put these things next to the capital H, it's not a literal multiplication in G. Though this is defined using multiplications, products. Same thing here. This plus sign is when the group operation is addition, is the group operation, that plus. This plus is just notation. This is notation, well, in general, C plus H is going to be the set of all elements of this form as little h arranges over capital H when your group operation is addition. Examples. Well, proof that this is a group I'm not going to do. We don't have enough time today. We'll come back to this on Wednesday. Though I will mention quickly that you do have to show the operation is well defined, because the same coset can have different representatives. That's that same issue that came up with the proof of the orbit stabilizer theorem. Let's consider examples though. How about the factor group of Z mod the cyclic subgroup generated by 3? What are its elements? Its elements are the left cosets of this subgroup in the whole group. For example, the subgroup itself is a coset. You can also think of it as 0 plus the subgroup. As a set, that is, of course, this set. It's the hardest thing to get over about factor groups. The elements of the factor group are sets. The factor group is a set of sets. The next element is 1 plus the subgroup, that left coset. As a set, that consists of these numbers. But as an element of the factor group, it is one element. This consists of these elements, this set. These are all three distinct so far, but it represents one element of the factor group. Are there any other elements? No, this does it. 3 plus the subgroup is the same as the subgroup. Right? It gets sucked in there. I will not make a slurping sound. Gets sucked in. This is the same as that set. 4 plus the subgroup. If you like, you can think of it like this. And the 3 gets sucked in. Maybe I should practice my slurping. Don't slurp during the test, okay? But maybe before next time I'll practice my slurping, so it'll sound better. The 3 gets sucked in, because it's in there. It's in that set. Right? We have this abstract property of cosets. AH equals AH if and only if A is in H. That's the property I'm using, except with addition instead of multiplication. This is giving us nothing new when we do this, when we keep going like this. That gets sucked in. This is the same as this. So this is a 3-element group. It's got to be isomorphic to Z3. It's got to be cyclic. And it is. Can we make its Cayley table? Sure. Oops, I don't want commas. Zero plus the subgroup. The subgroup itself is the identity. You can quickly fill in this part. What's this thing added to itself? According to, well, what I had on that other slide. This thing here, except with additive notation. The sum of this thing with itself, I need to add the coset representatives, just like I'm multiplying the coset representatives here. I need to do 1 plus 1 plus the subgroup generated by 3. Gives me this. If I add these two things, same kind of rule. I got to add the coset representatives 1 and 2 to get 3. But 3 is in the subgroup. This is the same as the identity element. This group is abelian. You'll get the identity element here too. And here 2 plus 2 is 4. But 4 is 1 plus 3. The 3 gets sucked in. Get that. This is cyclic. It's generated by both of these elements. Those are your two elements of order 3. And you can write kind of crazy looking equations that look things like this, say. Okay, kind of weird, but this is valid. Almost out of time. Let me just end by saying, giving a few applications, so to speak. We'll go into more depth on Wednesday. There's something called the GZ theorem that says if the factor group G by the center of G is cyclic, then G actually has to be abelian, which is actually kind of strange if you think about it. This actually implies that if this is cyclic, it must be trivial. Therefore, if this factor group is not trivial, so that G is not abelian, then this thing cannot be cyclic. It's got to be some non-cyclic group. Interesting. And therefore, as an application of this, if G is not abelian of order the product of two primes, P and Q, then the center must be trivial. Because if the center were non-trivial, it would have to either have order P or order Q. If it had order P, it turns out the factor group would have order Q, which means it would be cyclic. That can't happen. That's an interesting thing that's worth noting as well. These are applications to group theory itself, not necessarily thinking about real life application. Okay, see you Wednesday.